Okay, so we start a new section, some linear algebra. It's titled. So in this section, the author is going to link some notions of linear algebra to graphs somehow. Let us see how. It starts up like this. Let G equal to V comma E be a graph with n vertices and m edges, and in fact let the vertex set V of G be this V1, V2, etc. to Vn, and similarly let the edge set be one such set E. Okay. Now the vertex space nu of G of the graph G is defined to be the vector space of all functions from V into F2, where F2 equal to 0, 1 is the two-element field. Okay, so what is being said here? So G is our ordinary graph. It has a vertex set, it has an edge set, and the way these sets have been written, the way their elements have been shown, you can clearly see that the author has meant them to be non-empty, both V and E. Now the vertex space nu of G of the graph G is the vector space, is defined to be the vector space of all functions from the vertex set V into this two-element field consisting of 0 and 1. So what do all these things mean, and exactly how is this set a vector space? What are the operations? Now those of us who are familiar with, most of us are of course familiar with linear algebra, but you may have forgotten these things. So let us briefly see how this is a vector space. It's a very natural fact from linear algebra, but let's see exactly how this is a vector space. So the thing here is this. Say you have a non-empty set S. The elements in S can be anything. Okay, it does not matter. It may not even be numbers or vectors or in fact anything mathematical. Its elements may be chairs, tables, anything. On the other hand, let F be a field, any field. Now with these two objects, what we do is we consider the set of all functions F is a function from S into the field F. That means all functions are being considered whose domains are equal to S, and the functions are taking their values in the field F, and the set of those functions is V. Now one can clearly see that V is non-empty because S is non-empty, but even when S is empty, still V is non-empty, but we are not going to go into such trivial complexities, okay, because we are not considering functions from an empty set, from the empty set into F2, but rather from the non-empty set of vertices into F2, and that's why I said here that V is non-empty. Okay. Now, among the many possibilities of functions, I mean elements that will be there in V, there is one particular function which we can see is in V and which we will need also to see these things. Consider the function 0. We are using the symbol 0 just to denote the fact that it is somehow linked to the 0 element in F. Consider the function 0 from S into F, whose definition is just this. And this S is of course coming from the set S. So that means this function is constantly 0, and this 0 is of course the field 0 element from the field F. And this 0 function belongs to V. Okay, so that means our V is a non-empty set. Now next, so what we are trying to show is that this V, just like this one, is naturally a vector space over F. What are the operations? Let's see the addition first. Say we have taken two elements F and G in V. So that means both F and G are functions from S into F. Now we want to define their sum. That means we are trying to define an addition operation on V. Whatever this sum turns out to be ultimately, we want this sum to again be in V. That means we want this sum to itself be a function from S into F. Now this is the natural definition of that sum. It's a symbol for the sum. And so that means the way we have written it, it should be a function from S into F. What is its definition? Its definition is that if you evaluate it at any element S in S, then this is equal to F of S plus G of S. And you can immediately see that all of these things make sense. Why? That is because if you are taking an element S from S, then since F and G themselves are well-defined functions from S into F, so F of S and G of S are unique field elements here, and hence their sum is also a unique field element. You can see that their sum, I am saying, that's because this sum is the ordinary addition operation that you have in the field, and that is why F plus G is itself a well-defined function from S into F, and that proves that F plus G is in V. So at least the sum we have defined is such that V is closed under it, and from the look of this definition you can almost immediately see that this sum will also be associative, because the ordinary field addition is associative, and this will be the 0 element for this sum. If you add 0 with F in any manner, that is F plus 0 or 0 plus F, that you will see ultimately gives you F itself. So this is your additive identity. What about additive inverse? Say for your F in, where is it? F in V, I want to define a function which will act as the additive inverse of F with respect to this operation. So I define I am using a symbol like this minus f. I am defining again a function minus f from s into f. Whose definition is this? When you evaluate minus f at any element s from your domain S, then it is defined to be equal to minus f of s, where minus f of s means that f of s is of course your field element, that is the value of the original function f at the input s. Minus of f of s means the additive inverse of the field element f of s, which is again a unique element in the field. So this minus f is also a well defined function, and it also belongs to your v. And this function in fact is one such function, so that if you calculate f plus minus f and minus f plus f, you get this zero function. And all of these things now tell you that v is a group under this addition. One more thing that you can see is that because field addition is commutative, this addition is also commutative, making your group an abelian group. Okay, so V now has been turned into an abelian group. I want to keep these things for some time. Let me instead wrap this part of here. But only addition is not enough. You want an external operation also, that is multiplication by scalar. So what will you do? How will you define multiplication? That also will be defined in a very natural way. Say you already have this f from V, and now you consider a scalar alpha from f. I should not perhaps say scalar at this point because we have not yet shown that this is a vector space. I should just simply say a field element alpha. Now I want to define a function alpha f. I want that to be a function from S into f. That means I want it to be an element in V again. And its definition is this: alpha f of S is defined to be equal to alpha times f of S. Does it make sense? F of S is the field element that you get by applying f to S, and alpha is also a field element, so this is their product in the field. So here we have used, just like here we have used the addition operation in the field, here we are using the multiplication operation in the field. And you can also, just like this one, see pretty easily that this alpha f is in fact a well defined function. So alpha f also belongs to V, and one can then go on to show that the other four axioms that are there in the definition of a vector space are satisfied for these two operations, turning the whole system into a vector space. So this is that vector space that we are talking about here. Its elements are also functions, but here in place of S you have the vertex set of the graph, and in place of the field you have not just any field but the two element field having 0 and 1. Now for those of us who may have also forgotten what this field is all about and all these things, let me just say something briefly about F2 also. It's the smallest possible field. The thing is that you may think, how many different areas of mathematics do you need to remember? There is no clear-cut answer to that, but at least you should be familiar with the basic notions from all the areas, no matter what the area is, whether it's an algebraic area, an analytic area, a geometric area, or even some of the applied areas. Now, being familiar with something does not mean that the moment someone asks something about that part to you, you immediately should be able to give them some answer. No. Being familiar means that you may have forgotten about these things, but when you see them again once, all the things come back, or a significant portion of whatever you learned previously about those things, that comes back. Okay, then it's okay, then there is no problem. Now, there are two ways of looking at the field having two elements. One of them is, of course, just the absolutely mechanical way of treating these 0 and 1 as abstract objects, which we do every now and then in mathematics, because that's what we do all the time, treating things as abstract objects having some properties. So, to turn F2 into a field, you will need one addition and one multiplication. So, those two operations can be just simply defined, okay, like this. 0 plus 0 is defined to be equal to 0. It may look foolish, 0 plus 0 is defined to be equal to 0. No, you may say something like this: I already know 0 plus 0 is 0. No, you don't know. This 0 is not ordinary 0, it's just an abstract symbol. So, unless we define what 0 plus 0 is, this 0 plus 0 expression is meaningless. But now its meaning is 0. Just like that, 0 plus 1 is defined to be equal to 1, 1 plus 0 is defined to be equal to 1, and 1 plus 1 is defined to be equal to 0. This part tells us that this 1 is not our ordinary real number 1, because real number 1 plus 1 is never equal to 0. Then, like that, there is our multiplication operation. 0 dot 0 is defined to be equal to 0. I do not want to write 0 0 because it would look somewhat confusing. So, I am writing dot. 0 dot 1 is also defined to be equal to 0. 1 dot 0 is also, its meaning is 0, and 1 dot 1 is defined to be equal to 1. And one can then again go on with all the axioms mechanically and show that under this first operation as addition and the second operation as multiplication, this is a field. Okay, that's the absolutely mechanical way of looking at this system. There is another way of looking at this. You know that on the set of integers there is an equivalence relation, and that equivalence relation is congruence modulo 2. What that relation is, the definition of the relation is just this. Say you have any two integers a and b. We say that a is related to b if 2 divides the integer a minus b. In the language of congruence, this divisibility relation is written as a congruent to b modulo 2. It turns out that this is an equivalence relation, and it partitions the set of integers into disjoint equivalence classes. Now, it turns out that in this case, for this particular relation, there are only two equivalence classes. One of them is the set of all even integers, which is denoted by this symbol, and the other is of course the set of all odd integers, which is denoted by this symbol. In some texts, these same things, these classes are also denoted like this, 0 bar and 1 bar. Same meaning, different symbols, different names. And equivalence classes have their own addition and multiplication, under which this set of equivalence classes becomes a ring. And this, in fact, what I am saying is in general true, not just for 2 but any positive integer n, which you may already know, or it may be coming to you from a course that you already took sometime in the past. And when the modulus is n, there are n equivalence classes. In this case, there are 2 equivalence classes. No matter what n is, there is an addition of equivalence classes and a multiplication, under which that set of equivalence classes is a ring. Now, when the modulus is 2, or in fact a prime number, it becomes a field. So you may say that, okay, these two are things are different. No, this 0 is an abstract symbol, 1 is an abstract symbol. Here, however, they have some other meaning. Okay. However, these two fields, this field is written like Z2. They are isomorphic, and in algebra, isomorphic structures are actually the same thing. They are only labeled or named differently. So that is what your F2 is. Okay, so now fine, so we have got a vector space associated to the vertex set of the graph. So what can we now say about this vector space? I think now we can get rid of this part. The first thing one notices is this. That as sets, this vector space is, as a set, this vector space nu of G has a one-to-one correspondence with the power set of the vertex set V, or sometimes this same thing is denoted by a symbol like this. Okay, that means there is a correspondence between the functions that you have in this vector space and subsets. So that is the next thing the author is talking about. So let us write word by word what Diestel has written in the text, and then we will try to understand why these things are true and what is that correspondence in fact. So Diestel writes like this: every element of our vector space nu of G corresponds naturally to a subset of V. And in fact, which subset, that also he says, the set of those vertices to which it assigns 1. The set of those vertices to which it assigns 1, and conversely, every subset of V is uniquely represented in our vector space is uniquely represented in the vector space nu of G as the indicator function by its indicator function. Okay, so what are we saying here now? Every element of the vector space naturally corresponds to a subset of the vertex set V, and it corresponds to that set of vertices to which the function assigns the value 1, and conversely every subset of V is uniquely represented by its indicator function. Now what are these things? So let us try to understand this with a diagram. It's not necessary to draw a diagram, but every time you draw a diagram you can see all the things at once. And if you are not able to understand something that involves functions, you should always draw the arrow diagram that we generally draw to represent functions pictorially. Okay, so this is our situation. So what is our vector space? None of these two sets is our vector space. Our vector space is in fact the space of all functions from V into F. Every element of nu of G. So let us take one element of nu of G. Say F is in nu of G. F is a vector. Actually F is a function, but you can also call it a vector because it's coming from a vector space. So this F is a function from V into F2. Now what Diestel is saying is that this function naturally corresponds to a subset of V, namely the set of those vertices. Here we have the vertices of the graph. Those vertices to which it assigns 1. Okay. So these vertices are assigned to 1 by F. That means each one of them is mapped onto 1 by F. F of each one of them is equal to 1. Whereas there are possibly some other vertices, each one of which is mapped onto 0. So the author is talking about this subset of V, and looking at how the subset has been defined, you can in fact write something for the subset. If you look carefully, this is just the set of all pre-images of 1 under F. That means this subset is F inverse of 1, and the other subset is F inverse of 0. Okay, so this is the subset we are talking about here. And conversely, okay, now there is a converse also. If on the other hand you are not starting with a function, but rather you are starting with a subset of V itself, so this is one thing. On the other hand, say you have a subset U of V. Is this U coming from such function in this manner? Yes, and that function is the indicator function of U, which is defined like this. The indicator function, usually there is a notation for this, it's written as 1U, like a 1 suffix U, is a function from V into F2, and its definition is this. The value of the indicator function, and because we are having a vertex at V, if you want you can write Vi here, but let's not make matters complicated. Let's just simply write V. The value of this function at V is equal to 1 if V belongs to U and 0 if V does not belong to U. Okay, so that is the indicator function of U. Why is it called the indicator function of U? Because it tells us precisely what the elements of U are. How? By looking at which elements are getting mapped onto 1, because they are precisely the elements of U. The others which are not in U are mapped onto 0. And you can clearly see that this, in fact, if you are given a subset U, this in fact is a well-defined function. You take any element V from V, that element is either in U or not in U. Exactly one of these two possibilities is true. So the value is either just 1 or 0. So you are getting a unique value, and that value of course is in your field. So this is a well-defined function. So this indicator function 1U is in fact in your vector space this. However, does it really associate U in this manner? I mean, whatever we are seeing here, U to 1. That is, if now we are concentrating on 1 and say we want to say that 1U, just like here F made the correspondence between 1 and this set, 1U should make the correspondence between 1 and U. Yes, because from the definition of 1U, you can clearly see that the inverse image of 1 under 1U is actually equal to U. That is, we have this. You have this 1U inverse of 1 is equal to U. From your function theory, recall that this notation F inverse of 1 is valid even when actual F inverse may not exist, because F may not be a bijective function, but see, we are, the interpretation of this symbol is not the value of one, the value of f inverse at 1. This is not the meaning of that. It means the set of those images in the domain, all of which are mapped onto 1 by the function f. Yes, of course, when f becomes a bijective function, then those two meanings in fact are the same. But anyway, here we have this. So we have set up a one-to-one correspondence between the vector space elements and subsets of V. And in fact, this correspondence is just that. You take any element f from your vector space. This f corresponds to the subset f inverse of 1 of V. That means you now have a function t from your vector space into the power set of V, P of V, or 2 to the power V, whatever you want to use to denote the power set. And one can quite mechanically, in a straightforward manner, prove that this function is in fact bijective. And that is why there is a one-to-one correspondence between the vector space and the power set of V. Now, between the vector space and the power set of V, where the vector space is just a set, in this correspondence T, the operations in nu of G, they have not made any appearance. There was no need. However, can we extend things now? That is, you are using a flashlight T to map nu of G into P of V. Now, can you use the flashlight to not just map the elements of this into this, but the operations also? Well, at least you can do that for addition in this way. That is the next thing. You can understand that just like two functions in nu of G can be added together to give you a third function, the corresponding images of those two functions in the power set, that is two subsets, can they also be added similarly? So that this association T is respected. Technically speaking, can we define a plus on P of V itself that will at least turn P of V into a group, so that this T is a homomorphism? Yes, we can. And that's where this next thing comes. All these things have been mentioned very loosely like this. We may thus think of our vector space nu of G as the power set of V. Made into a vector made into a vector space, not just as a group but as a vector space. Anyway, let's see what the author has written, and then we will try to understand that in this way. The sum u plus u prime of two subsets u and u prime of v is their symmetric difference. See just how interesting this is. Here we have a natural addition. Now if you use T to define an addition on P of V, then it turns out that that operation on P of V is the symmetric difference that you have among subsets of a set. But how is that true? Let's see. Let u and u prime be subsets of V. According to our correspondence T, what are the corresponding functions? Namely, the indicator functions of u and u prime, to which they correspond respectively. These sets, they correspond or are represented in the vector space nu of G by the indicator functions. In fact, that's how the author has written. These sets correspond to their indicator functions 1u and 1u prime in the vertex space respectively. Now what does this mean? We may think of this as as the power set itself of V, that means as P of V, made into a vector space where the sum of two subsets is their symmetric difference. What this means is that, okay fine, so we don't know what the sum should be in P of V. That should correspond to the sum that you have here. That means the sum between these two functions. Their versions in the vector space nu of G. I mean the versions of u and u prime in nu of G are these indicator functions. So now what we are saying is that if we take the sum of these two functions using the sum that we have here, that is sum of two functions, then we will get a function that in fact will turn out to be the indicator function of something here, and that something is the symmetric difference of u and u prime. Let us see if that is true or not. Now the claim is that one u plus one u prime is the indicator function of the symmetric difference of u and u prime. That means that is equal to 1 u delta u prime. I don't know whether, or I don't remember whether the symmetric difference of two sets has been assigned any symbol in this book or not, but I am denoting the symmetric difference of u and u prime by this symbol, where u delta for difference, this is of course your ordinary symmetric difference, is the symmetric difference of u and u prime. How to see that? So what do you need to show here? You just need to show that these two functions, the one on the left and the one on the right, they are identical, that is, they must have the same outputs for a given input. So let phi belonging to v be any element okay. Now some possibilities will arise. If v does not belong to u union u prime, should I write like this? Or okay, not union. Why union? I can directly write the difference itself. U does not belong to, say V does not belong to the symmetric difference. Then what? To make things still again easy for us, let us draw the symmetric difference. So the symmetric difference of u and u prime, see, the situation is like this. This is our u, this is u prime. There may be an intersection, the intersection may also be empty, and this is our v. So if okay, so now what is the symmetric difference? Symmetric difference is u minus u prime union u prime minus u. That means this is u minus u prime and this is u prime minus u. Now v not being in this set means either v is here or v is here. Either v is not in the union of u and u prime at all, or v is sitting in the intersection of u and u prime. So accordingly, what will you get? Then let's just write that itself. Then either phi does not belong to u union u prime, that case is this one, or phi belongs to u intersection u prime. Does not belong to, belongs to, keep that in mind. If V does not belong to U union U prime, then V of course is neither in U nor in U prime. So what will these things be? What is the indicator function of U value at V? This is equal to 0 and this thing is also equal to 0. Naturally, because V is in neither of them. On the other hand, if V belongs to their intersection, that is the other case, then V belongs to both of them, equal to 1 because of that, and the other value is also equal to 1. So either now what we do, using these values we calculate the value of this sum at V. By the definition of sum, this is equal to 1 U of V plus 1 U prime of V. So in the first case, this is 0 plus 0, which is equal to 0. Keep in mind, this 0 is your field element 0 in F2, not ordinary 0. Or in this case, both of them are 1. However, in our field of two elements, 1 plus 1 is actually equal to 0. So in both of the cases, the value of this at V is 0. I do not want to lose this part as yet. On the other hand, if V belongs to the symmetric difference, then V is either here or here. U difference U prime or U prime difference U. Accordingly, okay, when V is in U difference U prime, that means what? V is in U and not in U prime. So in this case, 1 U V will be equal to 1 and 1 U prime V will be equal to 0. Whereas in the other case, where V belongs to U prime minus U, it is in U prime but not in U. So in that case, 1 U V will be equal to 0 and 1 U prime V will be equal to 1. So what do you have? I can write whatever I want to write here, still in just this much space. So 1 U, now I am going to be a little brief. This is going to be what? Of course 1 uv plus 1 u prime v. But now whether the case is this or this, one of the values is 0 and the other value is 1, and their sum in your field is equal to 1. So do you see what we have what we are seeing here, that if the vector v that we have arbitrarily chosen from our vertex set, in all these things do not forget that this v is actually the vertex set of the graph. Then if that vertex does not belong to this symmetric difference, then the 1 u plus 1 u prime value of that vertex is 0. Whereas if it belongs to the symmetric difference, then the value is 1. So this 1 u plus 1 u prime is nothing but the indicator function of the symmetric difference, and that is why we have that thing. That is 1 u plus 1 u prime is equal to 1 u delta u prime. And if you look a little more carefully, this actually is, it just tells us that that correspondence T which we have between our vector space and the power set of V, which makes any subset U or any element in P of V correspond to its indicator function. This correspondence, I give a two-way arrow because this is a bijection or perfect matching. So this indicator function, this correspondence and this equation tells us that this group is isomorphic to this group, because you see that what is this 1u plus 1u prime? It is well, I am taking things from this side to this side. Okay, fine. It just tells us that T inverse U plus T inverse U prime is equal to T inverse U delta U prime. This delta is the operation in this group, and this plus is of course the operation in this group, proving that T inverse is a homomorphism, and because it is bijective, it's an isomorphism, and that is why T is also an isomorphism between these two groups. However, not just groups, the author is mentioning that the vector space structure of this also gets mapped onto here. That means following the scalar multiplication that you have here, you can have a corresponding scalar multiplication here, about which however he does not say anything more. Maybe because that scalar multiplication does not translate into something, some operation that we already know is there in the power set of V. But that is there, that thing is there, although it may not look so nice like this, or it may not be expressible in terms of something that we already know. Okay, so in a rather very strange way, this is also a vector space, the power set of the vertex set of the graph, and all these things now tell us that these two vector spaces are isomorphic, and that is why the author is saying that we can think of our vector space as just the power set of V, in which addition corresponds to symmetric difference of subsets. and these things are simply not being forced upon us, because if we just simply have a vector space associated to a graph and nothing else, then it's pointless. Mathematically it's pointless, but the properties of that vector space are somehow linked to properties of graphs. Now let me just put some ink and let me just say a few more things and then we will start. If you see in the text itself, just a few lines have been devoted to this part. However, we are taking this long because we want to understand all the things in full detail. Oh, and by the way, what is the zero element here in this vector space P of V? To see the zero element, of course, you do not have to see the full vector space structure. You just need to know the zero element of the group structure. Viewed in this way, the empty vertex set, the author writes, because we are treating it as a subset of V, is the zero in P of V, and for any U subset of V, or we can just directly write for any element U in P of V, its additive inverse is just U itself, and these things can be verified without going there. You can just directly see them in the symmetric difference itself. In fact, let me just show you. If you, for example, calculate the symmetric difference of an element U and the empty set, what do you get? U difference the empty set union the empty set difference U. Now this is nothing but U, and this is the empty set again. So you get U back, and in that sense this is the zero vector in this vector space, and every element is its own additive inverse. That is also pretty easy to see. So you get the zero element. That's fine. Okay, now since this is a basis of nu of G, namely its standard basis. The dimension of our vector space is n. Now what the hell is this? See, immediately after saying that we can think of our vector space nu of G as just the power set P of V of the vertex set of the graph, the author has actually done that here. Because the elements that you see in this basis are strictly speaking not elements in our vector space nu of G, but rather elements in the power set of V. So that identification between nu of G and P of V has been used here. And this is and because of this fact, the dimension of our vector space or of P of V, same thing because they are isomorphic vector spaces, is n, the number of vertices in the graph, or the order of the graph, in other words. Now, just like all these things, exactly how this is true and in what sense we can make sense of all these things, that we will see in maybe the next, not maybe, in the next graph theory video. I do not want to extend it anymore. I think it has already been quite long. Further things are also there, which one can means we will define, namely between two vectors, that is between two subsets U and U prime of V, or correspondingly between their indicator functions, we can define a sort of product, which the notation looks like inner product, although it is actually not an inner product because the field involved is neither the field of real numbers nor the field of complex numbers. But still, using this product, then next, so I am saying what the things that are going to come next. One then defines this thing for a subspace f of your vector space u of G, and it turns out that the dimension of your f and the dimension of your f perpendicular, if you add them, then you get n. Well, this however is not defined for the vector space, I mean the vertex space, but there is another vector space like this. Whatever we did here for the set of vertices, exact similar things can be done for the set of edges also. Okay, so that corresponding vector space is called the edge space. For any subset or any subspace f of that edge space, which is written like this, epsilon of G, such things can be defined, and then these vector spaces, their properties are somehow linked to graph properties. That we will see in the next video. So I am ending things here itself. If you have any doubt about these things or any other thoughts you may want to share, you may write in the comment section below, or you can mail me. The address will be there in the description. And tomorrow what? Tomorrow we have already once again gone through Lee's algebra problems, right? So tomorrow let us again go to Gallian's group theory problems, and then we will see where we can go from there. So that's just it. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical room, signing off. Have a nice night.